So today in class, I talked to you guys about the process that we're going to use to balance redox reactions, and now I want to give you guys a couple of examples. And my other class, actually the D block class, got the first one, so this is going to be a little bit of a repeat. You can move ahead in the screencast to look at the second example, but this is example one, and so this really benefits my D block class more. I'm sorry, my C block class more than my D block class. So here's the reaction. I'm just going to take a moment to write it out. One thing I want you to notice right away is that I have an ion of Fe, another ion of Fe2 plus there, and then an ion of the Al3 plus. And what's vital for you to understand here is that you wouldn't just have these ions by themselves. They would actually have an anion associated with each of them, but I've chosen to eliminate them because each of those anions are simply spectator ions. So there's no point in putting them in there, and in some ways it greatly simplifies this process for you. That doesn't mean I'm always going to do that, and as you'll see in subsequent problems that you guys are going to do in class. But for now, just to give you the initial one, it's easier if I leave it out. So first thing we need to do is go through and assign oxidation numbers. So my iron is going to be a +3. My aluminum is going to be a 0 because it's an elemental form. Then I have a +2 iron and a +3 aluminum ion over here. Now, we need to figure out what the oxidizing agent and the reducing agents are, and we always look to the reactant sides for this. And if we look at our Fe, we know that it starts off as Fe3 plus with a +3 oxidation number and ultimately ends up as an Fe2 plus with a +2 oxidation number. And as a result, we understand that it's gained an electron in that process. And the only way that you can make it reduce itself in this process to go from a +3 to a +2 is to gain an electron. All right, so if it gained an electron, then it must be the oxidizing agent. Okay, because the oxidizing agent is going to be the thing that takes it. If you recall, that's the mean guy who's saying gimme in the notes that you probably are taking just below or above these notes here. Okay, and then we look at our aluminum, and our aluminum goes from Al, and it's in its elemental form, so it has a 0 as an oxidation number, and it becomes Al3 plus, which is a +3 oxidation number. And this is a loss issue. The only way that you can become a higher number is to lose electrons so that you become a more positive number. So that means this is the reducing agent because it gave away its electrons. This is the happy guy who's saying take. All right, so we've just given ourselves a little bit of a hint as to what's going to go on. The next step we need to do is create our half reactions from this. So you look at this big equation here and you focus in on each aspect of it. So we're going to start with our Fe3 plus, and we know that's going to end up as Fe2 plus. To make this whole reaction work, notice that this is the thing that's actually reduced, and if it's reduced, that means that it has taken on an electron to become reduced. So we have to add one electron over on the reactant side of this so that it can become Fe2 plus. So it goes from Fe3 plus to Fe2 plus. And then we're going to do the same thing for aluminum. And we know that ultimately has to become aluminum 3 plus. And in order for this to be the case, then it must have given away its electrons in order to become Al3 plus. So instead of adding electrons to the aluminum side over here, we're going to make sure that we put the electrons over here because they've broken away from the Al and they're being given up. Okay. Now, in this case, in order to go from Al0 to Al3 plus, it's not just one electron that you need to get rid of. you need to get rid of 3 electrons. So it's important that you make sure that your half reaction reflects the exact number in the change of your oxidation numbers. Okay? Now, the other thing I want to point out to you here, I forgot to do this earlier, is if in the old ways, if I had said go ahead and balance this equation, you would have looked at this and said, well, it's already balanced. I have one Fe on this right here, and I have one Fe over here, one Al, so that means it must be done. We're in balance. Well, that's the thing with redox reactions. You can't just look at it and balance it in the conventional way, which is why we're doing the crazy thing we're doing right now. Okay, so the next thing I want you to look at here is the particles themselves are correct, right? The number of particles. We have one particle of Fe with one particle of Fe, so we don't need to put any coefficients in to change things. Similarly, the aluminum and the aluminum showing coefficients of 1, that's all in order, so we can pass on that. But what we don't have in order is the correct number of electrons. And recall that the first rule is you have to have the same number of electrons that you gain as you lose. And in this case, that is not the case. So to balance things, we simply multiply this top half reaction by 3. That's going to allow us to have then 3 electrons associated with this top half reaction instead of just 1 electron associated with this top half reaction. So we have 3 Fe3 plus now plus 3 electrons yields 3 Fe2 plus. So all I did was put coefficient here, coefficient here, coefficient here. And now the easy part comes up, which is simply to combine these things all into one. So if I'm going to combine these ones that I'm boxing up in green, okay, that leads me to writing 3 Fe3 plus 3 electrons plus the aluminum. And in fact, I should probably put in the states of matter here. And that will give me 3 Fe2 plus the aluminum ion, which is a 3 plus ion in this side, plus 3 electrons. Do you see the 3 electrons that I have over here? Okay. 3 electrons that I have here went to here. 3 electrons I have here went to there. And then we just need to simplify things. So we can see that these 3 electrons disappear, and that simply leaves us with having 3 Fe3 plus Aq plus Al solid goes to 3 Fe2 plus Aq plus Al, which is also Aq, 3 plus. And there you have it. So what I'm boxing up here in red is a balanced redox reaction. A little weird, huh? So let's take a look at the second one. And for those of you who are in my D block class, this is going to be a new one for you. And we're going to look at something that you could have balanced no problem in a conventional way. However, I want you to do this now in a redox way. Okay, and that is the formation of salt. Again, process we need to do there is to go through and assign the oxidation numbers to everything. So the sodium in this situation here is in its elemental form, so that's 0. The chlorine also is in its elemental form as a Honkelbrief, it's diatomic. However, if we take a look at the Na and the Cl over here, the Na is going to be a +1 because it's an alkali metal, and the chlorine we know is a halogen, which is going to be a -1. So that was pretty easy to set up our oxidation numbers. And then we're going to go ahead and put together our half reactions here. Oh, actually, I should be careful. No, let's do our oxidation and reduction agents. All right, so this one, here's our reaction that shows Na going from an oxidation number of 0 to an oxidation number of +1. That means it has to have lost an electron. If it lost an electron, then it's oxidized. If it has been oxidized, then it is the reducing agent because it's going to reduce the chlorine here. Let's do the same thing for the chlorine. And you can see here we have the exact same thing, but it's opposite. Chlorine goes from a 0 to a -1. The only way it can do that is to have gained electrons. And if it gains, then it has been reduced. And if it's been reduced, then it is the oxidizing agent because it caused this to be oxidized. All right, so let's take a look at the half reactions that we can pull out of this. All right, so if we have to show our sodium losing an electron, so it goes from being in this state of having the electron, we have to show it in this state where it doesn't have its electron with it anymore. And so we do that by showing the electron separate from the sodium, like so. Okay. And then we're going to do the same thing here with the chlorine. Now the chlorine's a little bit tricky here. All right, so the first thing I want you to understand is that we're going to go from having Cl2, right, and we're going to form Cl minus. Now, the reason this is tricky is because we don't have things in balance with regard to our particles. So the first thing we need to do before we start messing with the electrons is to first balance our particles. And really, it's a pretty simple thing here. If you go from Cl with a subscript of 2 to a plain old Cl ion, I think it's not too hard for you to see that I need to put a 2 in front of the Cl because you can only add coefficients, you can't add subscripts. So putting that 2 in there is really the crux to this whole problem. Because now, and when I look at this and determine the number of electrons I need to move over, that's going to change. Oh, first of all, don't forget to put the 0 for the oxidation number here and the -1 for the oxidation number over the chloride ion. So if this is the case, then you know that I can't just add 1 electron to this side in order to make it go to 2 Cls. I actually have to add 2 electrons. 2 electrons, because that's the only way you're going to be able to produce 2 chloride ions, both of which are -1. All right, so I hope you got that critical little step right there. Now you probably can see what you need to do next because that was the hardest part. So once you get past that step, you can see that this one up here needs to be multiplied by 2 because we need to have 2 electrons as a result of the 2 electrons we have here. So that gives us 2Na going to 2Na plus 1 plus 2 electrons. And then we can combine these two here that I'm squaring up in black. And when I do that, I have my 2Na, and that is Na solid, if I'm not mistaken from the first thing, plus my Cl2, which was a gas. And, oh, geez, left out the most important thing here. Got to make sure I put in my 2 electrons, and that is going to lead to the formation of 2 Cl minus ions plus 2 Na ions and the 2 electrons associated with that half reaction. And it's pretty easy to see that those 2 electrons can then disappear, leaving us with 2Na, and now I'm just going to leave out the oxidation numbers because I don't really need to have them in there for the final thing. And this is going to lead to, now notice here, I'm going to have 2 NAs and 2 CLs. And if we go back to our original equation up here, we know that it has to form NaCl together. So I'm going to go ahead and press those 2 together, but since there are 2 each, and the 2 can distribute to each component there, then I just do 2 NaCl, put the solid on there, and there you have it. It's the balanced equation there. Could you have done this in the old way? Absolutely. But if I ask you to do something through redox, I expect you to go through the half reactions to get there. All right, see ya.